Hi there, Rachel Chase here, and in this video we will look at how to calculate a confidence interval estimating your population mean when the population standard deviation is known. Keep in mind that population standard deviation known is shorthanded as sigma known. In order to calculate the margin of error, we have to use the formula given as such. The margin of error is equal to your z-score based off of a critical value times the standard deviation over the square root of n. If you recall back to our previous chapter, we learned that this is a scaled standard deviation for sampling distributions. So if you put the two things together, we're estimating our population data based off of sample data that we know. So this is using the approximate for our sample data. Now, the first thing I always advise, especially when you're relatively new to word problems, is read the question start to finish. Once you know the big picture, then go back and pull out the information as you need it. So before you try and jump in, just find out what they're talking about. In order to estimate the number of calls expected at a new suicide hotline, volunteers contact a random sample of 36 across the nation and find the sample mean is 42 calls per month. Construct a 95% confidence interval for the mean number of calls per month. Assume that this number is normally distributed and the population standard deviation is known to be 6.5 calls per month. So if we go back there, I'm just going to list out in order what they've told us. They said that we took a sample of 36, that our mean from that sample, in other words, that's x bar, our point estimate, is 42. We want to construct a 95% confidence interval, which means that CL is 0.95. We immediately turn that to a decimal. And also, if the CL is 95, alpha is the complement of that. So alpha is 0.05. They've also told us at the end to assume our standard deviation is known to be 6.5. So what other information can we find here? Well, based off of alpha, remember that the z-score you are looking for is based off of alpha over 2. So if you take 0.05 and divide that by 2, we get here 0.025. In other words, the z-score that we need is z of 0.025, which comes from our z-score table. So if we take a look at our z-score table, this is very similar to what we learned about in terms of working backwards by hand in the previous chapter. We're looking for the closest value we can find to 0.025. So we go inside this table until we find 0.25. And in this case, it's exact. That gives us a z-score of negative 1.96. Now, one thing that's a little bit different here is that negative number is really superficial. And the reason for that is if you look at your margin of error, you're going to get either a positive or negative number here, right? However, the actual confidence interval is equal to plus or minus that margin of error. So a lot of times you'll see instead of the negative being included here, they'll drop it because what happens when you add and subtract a negative number? It's the same thing as subtracting and adding. So if that's something that worries you, you can keep the negative here, but please keep in mind it's not significant if you chose not to include it. Now, visually, what's happening? Now that we've got all of this kind of side information out of the way, let's talk about what this looks like in terms of a picture. So we have our mean somewhere in here. You know, the mean of this distribution is in the center, but we're trying to approximate what's going to happen such that these two side numbers are x bar minus your margin of error and x bar plus your margin of error. And this means, since we want to be 95% confident, that this area is equal to 0.95. So as tempting as it might be to use the tools we learned about in Chapter 6, unfortunately it doesn't work the same way because we no longer have only population data. Now we're relying on this sample to be able to get these boundaries for us. How do you go about finding those boundaries? By plugging into your margin of error and then adding and subtracting. So if we plug into our formula, we get the margin of error equals our z-score times our standard deviation divided by the square root of n, which gives us negative 2.12. Then, to construct our confidence interval, you take your mean of 42 and add and subtract the margin of error that we found. So this is equal to two things. You're going to take 42 plus a negative 2.12 and 42 minus a negative 2.12. When you add a negative number, it's the same thing as subtracting, which gives us 39.88. And when you subtract a negative number, that's the same thing as adding, which gives us a positive 44.12. So how could you write this as a confidence interval? We would say that the population mean is bounded between 39.88 and 44.12. In context, we can be 95% confident that if we were trying to estimate the population mean number of calls to expect, it's going to be somewhere between 39.88 and 44.12 phone calls per month. So the idea is that based on this level of confidence, we are constructing our boundaries. So 95% of the time, our population mean will actually fall in this interval that we've constructed. Let's take a look at another example. The American Management Association wishes to have information on the mean income of store managers in the retail industry. A random sample of 256 managers reveals a sample mean of $45,420. Assume that the income of store managers is normally distributed and the standard deviation of this population is known to be 2,050. Construct a 70% confidence interval for the population mean. So let's go back and write down what we know. We have a sample size of 256 with a sample mean of 45,420. We know this is normally distributed, otherwise we would not be allowed to construct a confidence interval. These are not trick questions. The data you will be presented with is always normally distributed or approximately normal. Standard deviation is known to be 2,050. We want a confidence level of 70%, so that's 0.70. Now you'll notice here when you're dealing with these z-scores, you really can use absolutely any confidence level of your choosing. Though something to consider is a low level of confidence means you're less likely to actually be accurate with your estimate for your population mean. Now, on the other hand, if it doesn't really matter so much, you could drop down to something like a 70%. Realistically, though, if something was perhaps a life or death situation or anything medically related, you usually see very high levels of confidence, so things like 99% or even 99.9%. So back to this question, if our confidence level is 70%, our alpha is 0.30, which means that alpha over 2 is 0.15. When we go into our z-score table, you're going to look for the closest thing to 0.15 that you can. So it's looking like 1.04 is the closest thing away because this is 15 over and this is 8 under. So we're going to use a z-score of 1.04. Again, positive or negative, it's up to you how you choose to write that. So visually what's happening here, sketch a quick picture. We want 70% of our data to be in the center. This is going to be x bar minus e and x bar plus e. From here, it's the same process as before. Plug in our margin of error equals 1.04, the z-score, times our standard deviation divided by the square root of n, which gives us, since this is money, round it to 2 decimal places, we have negative 133.25. So to get our confidence interval, take the mean and add or subtract your margin of error. When we add our negative number, we get $45,286.75, and that's our lower bound, where our upper bound, when we subtract our negative number, gives us $45,553.25. So here, what can we say to conclude? We can be 70%, since 70% confident, that our population mean actually falls between this number and this number. Now, for those of you that prefer using the calculator to find out things like this kind of z-score, as opposed to using the table, you do have an option for that as well. If we take a look at our graphing calculator and you go under your distribution menu, we can use the inverse norm function here. When you use the inverse norm function, what you're going to do is put in the area to the left of what you need. So for example here, if 70% is in the middle, that means there are another 15% on either side, hence where this alpha over 2 comes from. So I'm going to tell it take an area of 15%, and in the standard normal distribution, you always have a mean of 0 and a standard deviation of 1. So if we went this route, you'll see that we get negative 1.04 if we round, which was the same thing that we had when we calculated our margin of error before. So whichever option you prefer as far as finding your z-scores, entirely up to you. Another option you have would be to use the calculator functions that actually give you the confidence interval start to finish. Now, if you're concerned about showing your work, you might choose to go about it this way instead. Those calculator functions can be found under Stat, then go over to Tests, and then you'll see here there's a whole bunch on this list. If you scroll down where it says intervals, for sigma known, since we always use z, there are several options here just to show you. We have z intervals, t intervals, which we'll just discuss in the next video, and proportion intervals. This is considered a regular z interval, so I'm going to select my z interval function and tell it what my information is. I have a mean of 2050, a standard deviation of 2050, a mean of 45,420, and our sample size was 256. We wanted a confidence level of 70% here. So when I calculate, this gives me my boundaries. And you'll notice that it's very close since the calculator does not have to round, and we did have to round to do this by hand based off of our z-score chart. We get very similar answers. Either of these would be completely acceptable. Whichever method you prefer, it's entirely up to you. Now, one thing to be aware of is you might still have to find the margin of error. So if you're doing this in the calculator, how could you find the margin of error if you chose not to go about it using the entire formula? Well, for starters, find out what the range of your data is. So I'm going to type that in, 45,553 minus 45,287, and then just divide that by 2. So you'll see that that gave us the margin of error. So again, whichever choice you pick, that's entirely up to you. So you do have some options here, so please keep that in mind. The last thing to discuss in this section is what happens if instead you need to look at a minimum sample size. Now, minimum sample size is a useful tool because if you were actually going ahead and taking your own samples, you want to make sure that the first time you take a sample, you do it right. Otherwise, you're going to have to start back at square one. For example, if you wanted to be a certain level of confident, but your sample was too small, that means you've not met the requirements. So let's say you needed to sample another 10 people. You're not allowed to just go ask another 10 people. That would be sampling bias. So you'd have to, again, start at square one. So if you want to know before you even begin what's the requirement, you can use the equation n equals, it's going to look very similar here, that z-score times sigma over E all to the second power. Now the z-score you can calculate whether you do it in the calculator or using the table. It's entirely up to you. So let's take a look at how we would do this. A student in public administration wants to determine the mean amount members of city councils in large cities earn per month for being a council member. The error in estimating the mean is to be less than $100. So in other words, you want to be accurate within $100 at a 95% confidence level. The student found a report by the Department of Labor that reported the standard deviation to be $1,000. Department of Labor is a big overseeing body, so you may consider that to be population standard deviation. So what do we know? We don't know what n is, that's what we have to find, but we have to estimate within $100 means our margin of error is 100. We know that the standard deviation is $1,000, and we want to be 95% confident, so 0.95, which means alpha is 0.05, and alpha over 2, right, so we're dividing there, is 0.025. So if you're calculating this in your graphing calculator, your z-score of 0.025 can be found as such. Under distributions, use your inverse norm function. And this time our area to the left is 0.025. And we still have a mean of 0, standard deviation of 1. Again, this is when you're dealing with just finding the z-score. So you'll notice that earlier when we did this on our table, we found a z-score of 1.96, which if we round here also matches what we just found. So those two things line up. From here, you can go ahead and plug in what you know into our formula for minimum sample size. N equals our z-score times our standard deviation divided by the margin of error, all of that squared. So if you simplify what's inside, you end up with negative 19.6 squared, which gives us 384.16. Now here's the catch. If you want to be a minimum of 95% confident and you only surveyed, right, it's so tempting to round this down. If you rounded this down to 384, technically you're no longer 95% confident. You might only be 94.9% confident. So if you want to be better safe than sorry, which is kind of always err on the side of the caution, then round these types of questions up to the nearest whole number. So if I ask you how many people do you have to survey, how many people is a whole number. This is very similar than when we were calculating things like the mean number of people for something, where here you actually have to ask that question to a person. You can't ask 0.16 of a person a question. So anytime you're calculating minimum sample size, whether it looks like it rounds up or down, you always round these up. So in our next video, we will explore how we calculate confidence intervals for situations where sigma is unknown. In other words, where you do not have your population standard deviation. See you in the next video.